In our earlier tape on pilot protection, we took a brief look at the basics of power line carrier. Now, in that particular tape, we were more concerned about what PLC can do for us than how it does it. Now, in this videotape, we're going to examine PLC equipment in more detail. First, let's go into the switchyard and look at the line hardware. This piece of equipment, which is connected in series with the line, is called a line trap or wave trap. The line trap may be mounted vertically or horizontally, like this. The simplest type consists of a large coil, that is, an inductor, made of conductor material and capable of carrying high load current. It must also be able to withstand very high values of fault current for short periods of time. As you already know, the objective of the line trap is to confine the injected carrier signal to the desired conducting path. That is, the transmission line between transmitter and receiver. The line trap or inductor is sized so as to provide a reasonably high impedance to the carrier signal, which may be transmitted within the frequency range of 30 kilohertz to 500 kilohertz. At the same time, the inductor must offer zero or very low impedance to the flow of 60 hertz power current, which may be, say, 800 amps at 230 kilovolts. The value of inductor chosen is usually quite small, about 2 millihenries. You will remember that inductive reactance is calculated from the formula XL equals 2 pi FL, so it is proportional to frequency. At 60 hertz, a 2 millihenry inductor will produce an inductive reactance, that is impedance, of approximately 0.75 ohms. However, at the carrier frequency of, say, 100 kilohertz, the impedance of this inductor will be relatively high, about 1,250 ohms. So the loss of carrier signal will be quite small. We can draw a chart showing impedance against frequency. You can see that this simple, untuned line inductor does offer a reasonably high impedance over a wide range of carrier frequencies. However, experience has shown that in certain installations, the inductance can create a high-frequency series resonance with capacitive circuits on the bus side, such as CCVTs, lines, transformer windings, and breaker bushings. The consequence of this is a drastic reduction in impedance and loss of carrier signal. Many line traps consist of a tuned resonant circuit with inductance and capacitance in parallel. I'm sure you all remember this circuit from basic electricity. The value of inductive reactance is chosen to be exactly the same as that of the capacitive reactance at the desired resonant frequency. If we apply a voltage across this parallel circuit, we find that the current flow in the supply lead is practically zero. This is because within the resonant circuit, current is flowing from the inductor to charge the capacitor, and then in the next half cycle, it is discharging from the capacitor back to the inductor. The resonant current oscillates continuously between inductance and capacitance. If the circuit contained absolutely no resistance at all, the current supplied from the source would be zero. As no current flows in or out of this theoretical circuit, it provides an infinite impedance to the flow of current. In practice, resistance does always exist, but the circuit still provides a high impedance at the tuned frequency. Let's look at a typical case. The value of the inductor here is 0.2 millihenries. You can already see an advantage. This is 1/10 of the value of the line inductor that we previously examined. This gives us the very low impedance of 0.075 ohms at 60 hertz, and so reduces associated losses due to flow of power line current. At a selected carrier frequency of, say, 100 kilohertz, the inductive reactance will be 125.3 ohms. So in order to provide resonance, we need to select the size of our capacitor so that it will produce a capacitive reactance of 125.3 ohms at a frequency of 100 kilohertz. We can calculate this from the formula. The capacitive reactance, XC in ohms, equals 1 over 2 pi the frequency in hertz times the capacitance in farads. This works out to a required capacitance of 0.0127 microfarads. But what is the effect of this capacitor at power system frequency? Well, at 60 hertz, the capacitive reactance will be equal to about 200,000 ohms. So we see that virtually all of the 60 hertz current will flow through the inductor, which has only 0.075 ohms. And what is the impedance of this combined resonant circuit at 100 kilohertz, the carrier frequency? Well, if we had a perfect resonance, that is, the theoretical condition with zero resistance in the conductors, then this circuit would provide infinite impedance. But the circuit does contain resistance, and in practice, the impedance to 100 kilohertz current will typically be around 5,000 ohms. If we plot the impedance against frequency, the curve looks like this. The value of impedance falls off sharply as frequency moves away from the designed resonant frequency. At the resonant frequency, the inductive and capacitive reactances cancel out, so that the characteristic is that of a resistance. However, as soon as the frequency is changed, as is often the case in carrier operation, the perfect parallel resonance of the wave trap will be disturbed, and it will become inductive or capacitive. From this curve, we can see that a small frequency change from 100 to 98 kilohertz will produce a highly inductive component with the consequent potential for series resonance with bus equipment. In order to avoid this potential problem, further resistance is added to the line trap. This actually has the effect of reducing the impedance at the resonant frequency, but improves the off-frequency operation by providing a resistive characteristic. The resistance is usually connected in the capacitive branch of the line trap, and its value is chosen to match the line characteristic impedance, say 400 ohms. This type of line trap is known as low Q. The high Q wave trap has lower resistance and therefore relatively higher quadrature or reactive component. Many carrier applications require several channels. By adding more circuitry to the line trap, it can be tuned to provide high impedance at two different frequencies, as shown by these curves. By yet further complicating the tuning circuit, line traps are now made available with 600 to 1,000 ohm impedance over a wide band of frequencies, typically from 100 to 200 kilohertz. Most of these tuned circuits allow for fine adjustment in the field. The test is conducted by injecting a high-frequency signal into the circuit and measuring the voltage drop across the line trap. This simple schematic shows one method. The signal generator provides the test signal at selected frequencies, and the line trap is tuned so that the voltage drop, as measured by a high-impedance voltmeter, is highest at the selected resonant frequencies. Where possible, the line trap should be disconnected on both sides, so as to prevent interference to the test from the line capacitance. Preferably, it should be removed completely and suspended, so as to be completely free of any interference. All of the tuning equipment, capacitors, resistors, inductors, is located inside the main inductor coil. A typical utility company test procedure is included in your workbook. Make sure you have access to instruction manuals and your own company procedures. before commencing any test or tuning of line traps. It is essential that the line trap be protected by a lightning arrestor, as the main inductor coil could become seriously damaged by lightning surges. The lightning arrestor is often placed inside the wave trap along with the tuning hardware. During faults, the large inductor is subjected to very strong mechanical forces which tend to force the coil apart. This may damage the end connections. Even in normal operation, the line trap runs quite hot due to the high current flow, and this can sometimes damage the tuning capacitors. If a capacitor does fail, the line trap will no longer be tuned to the selected carrier frequency, and this could cause misoperation in the event of a fault. Now, later in this tape, we'll see how to regularly check the carrier for signal power. Because of the heat in the trap and the operation of the lightning arrestor, the trap can become quite dirty after 1 or 2 years operation. The arrestor can be damaged by doing its job, and this may go unnoticed as it is out of sight. Regular cleaning and inspection is necessary to ensure consistent wave trap performance. Well, now at this point, let's take a break, and then we'll come back and look at coupling capacitors. For now, please switch off the tape and review this material in your workbook. We have discussed how to confine our carrier signal to the power line. And let's now see how this low power carrier signal, say 10 watts, is injected into the high voltage power line conductor. The coupling capacitor, abbreviated as CC, provides the means for power line carrier coupling. As you know, the value of capacitance is selected so as to provide high impedance to flow of 60 hertz power current. On the other hand, at high carrier frequencies, the impedance is low, so the carrier signal can pass easily into the line. Sometimes the coupling capacitor is supplied with voltage transformer circuits which are tapped off the low voltage end of the capacitor. This provides voltage indication and operating power for terminal equipment at the site. This arrangement is known as a capacitor voltage transformer, or CVT, or even CCVT. However, let's focus our attention on the carrier coupling. The terminal box is often located at the base of the coupling capacitor. It contains the capacitor grounding equipment, that is, the grounding switch, the drain coil, and the protective gap. Let's look at the function of the drain coil. As you can see, it is connected between the coupling capacitor and ground. It has an inductance designed to give low impedance at 60 hertz, but a high impedance at carrier frequencies. So the coupling capacitor is safely grounded by the drain coil. The high-frequency carrier signal is connected to the ungrounded side of the drain coil. This signal will pass easily through the capacitor to the transmission line, but it will be isolated from ground by the high impedance at carrier frequency of the drain coil. In essence, the transmitter voltage signal is applied across the coil between the line and ground. The signal current circulates through the power conductor, out to be captured by the receiver through the coupling capacitor at the far end. This is where only one power line conductor and ground is used to conduct the carrier signal. An alternative scheme may use a phase-to-phase connection. As shown in this schematic, the transmitter and receiver are coupled to two power line conductors at each end. The carrier signal is applied line to line. With this arrangement, the requirement for line coupling equipment is doubled. Let's get back to our carrier accessories as they are known. The drain coil is made of very light wire and therefore cannot withstand high current or survive high voltages such as lightning transients. This is why the lightning arrestor is installed here. It may be a gas tube protector similar to the type used on telephone circuits or on pilot wire protection. Alternatively, the lightning arrestor could consist of a simple spark gap, such as a spark plug. If the drain coil were to fail and become open-circuited, it would open the ground on the coupling capacitor. Full line voltage now appears on the protective gap. This fires and an arcing sound is produced indicating an open drain coil. At this point, the maintenance staff will have to hot stick the grounding switch closed and replace the drain coil and perhaps the gap. The carrier grounding switch connects the signal directly to ground and effectively prevents operation of the carrier system. This could also occur inadvertently due to protective gap failure, such as foreign material bridging the gap. Regular inspection of the carrier accessories is necessary. So now, with our carrier equipment connected to the coupling capacitor, we have a low impedance path for the signal to flow into the line. We would like to have a yet lower impedance at the specific carrier frequency so as to reduce coupling capacitor losses. This is achieved by connecting a tuning circuit between the carrier equipment and the coupling capacitor. This circuit is often located below or at least close to the capacitor and is known as a line tuner or line matching unit, LMU. The simplest type of line tuner would consist of a series inductor sized to give inductive reactance equal to the capacitive reactance of the coupler at the specific carrier frequency, say 150 kilohertz. This would produce series resonance with very low impedance to the 150 kilohertz current. Indeed, if the reactances were perfectly matched, the impedance would consist only of the ohmic resistance of the conductors. However, one single carrier frequency is not usually enough. Quite often we will transmit at, say, 150 kilohertz and receive at, say, 112 kilohertz. In this case, the tuner must provide low impedance coupling at both the operating frequencies. In order to achieve this, the tuning circuit becomes more complicated, with a combination of inductors and capacitances arranged in series and parallel. Remember, parallel resonance provides high impedance at its design frequency, in contrast to series resonance, which provides low impedance. These circuits are often known as filters because they allow only the desired frequency currents to pass. Connections between the many inductors and capacitors are made at the terminal board by metal conductor straps. For this reason, the initial test and tuning is often known as strapping. In yet a further development, the tuning circuit is designed to allow operation over a wide band of frequencies, say 100 to 300 kilohertz. Simplified, the circuit looks like this. The incoming signal passes through a variable inductor in series with a variable capacitance, and then passes through a shunt connection to ground through a parallel resonant circuit. Finally, it goes through another series resonant circuit before the signal connects into the coupling capacitor. The signal input from the carrier is via a grounded coaxial cable, which we have shown grounded at both ends. Some utilities ground only one end. Check your utility's procedure. Invariably, the tuning equipment includes a multi-tapped impedance matching transformer at the input end. This is needed to overcome any impedance mismatch which may exist between the transmission line and the power line carrier equipment. The LMU allows us to provide proper impedance matching during the commissioning stage. For example, suppose the characteristic impedance of the line is 300 ohms, and that of the incoming coaxial cable from the carrier equipment is 50 ohms. The matching transformer taps will be selected to give a 6-to-1 ratio. But why is this necessary? What would happen if the impedances were not matched? Well, the quick answer is reduction in signal power. When the signal passes into a part of the system where the impedance suddenly changes, some of that signal is reflected back up the line from whence it came. This reflected power robs us of some of the useful forward power that we want to send down the line. Reflection of a signal can be explained by a simple and familiar analogy. When you shine a flashlight through a glass window, most of the energy passes through the glass. Some, however, is reflected back to you. The reason for this is that the glass and the air have very different optical characteristics. And when the light beam leaves the air and enters the glass, some reflection occurs. In our communications circuit, reflection will occur at any point where a discontinuity in impedance takes place. For example, where a second line is tapped into the transmission line. Under certain conditions, the reflected signal may be in phase with the original signal. It is coming and going at the same time, so producing a standing wave. This is similar to the vibration of a guitar or violin string. The resonant frequency gives off energy in the form of sound. In our power line carrier system, we do not want any portion of the signal to resonate and give off energy. If this should happen, the energy would be radiated and therefore lost into space, instead of being transferred down the transmission line. In order to prevent this loss, it is important that impedance mismatch be reduced as much as possible. The LMU taps should initially be set as near as possible to the anticipated value of line impedance, usually about 300 to 400 ohms, and the impedance of the coaxial cable usually 50 to 75 ohms. To fine-tune the settings, you will need special test equipment, specifically a voltage standing wave ratio meter. The meter is usually connected into the circuit between the incoming coaxial cable from the carrier and the coaxial terminal connection on the LMU. A carrier test signal is injected at the appropriate frequency, and the meter measures both forward power and reflected power. The taps are adjusted so as to achieve the minimum value of reflected power. This is not so easy where several transmitters are connected operating at different frequencies. One way of handling this is to connect the LMU into a dummy resistive load equal to the line impedance and adjust the impedance matching at the carrier equipment for each different frequency. Make sure you follow the manufacturer's instructions closely. There is an extremely wide range of equipment and a great variety of test procedures. One particular utility company test procedure is indicated in your workbook. Study this carefully, but make sure you follow your company's procedure when conducting this test. If the VSWR test indicates that there is difficulty in matching the impedances, then we must check out the LMU. First, close the grounding switch, then check the connections inside the unit. Coming down from the base of the coupling capacitor, you should see a single insulated conductor called the lead-in wire. Though this is normally a low-voltage connection, it could rise to line potential if the drain coil fails. The lead-in wire may be supported on insulators or run in PVC conduit. It may even be run in metallic conduit, but this is not good practice, as the capacitance of the wire to ground will be larger in metallic conduit, and this extra capacitance could affect the tuning action of the LMU. Check the lead-in wire for corrosion, burn marks, or tracking, particularly where the wire comes close to the metal structure or cabinet. Next, examine the coaxial cable. In many companies, this is checked annually as a routine because coaxial cable is much more fragile than most other cables. Sharp bends, nicks, and crushing of the jacket can easily degrade its performance. The connection of the cable to the LMU is sometimes a problem. If a coaxial connector has been used, make sure the connection between the braid shield and the body of the connector is solid. If the connection is hardwired, check for high impedance paths to ground and burn marks between the center and the shield of the coaxial cable. Okay, now that we have looked at connection of the carrier signal to the power line, it's time to consider the signal itself and look at potential losses. First of all, let's take a break. Please switch off the tape now and go through this material in your workbook. Let's look now at the carrier signal itself. How much power are we talking about? What is the typical value of signal power loss, and where do these losses occur? First, consider this simple on-off scheme, a blocking signal for pilot relaying. When the protection relay at station A operates, it switches on the transmitter, which is already tuned to send a signal at the desired carrier frequency, say 150 kilohertz. The signal power leaving the transmitter will be typically 10 watts, but other levels of power are also utilized. This high-frequency signal passes through the line matching unit, the line coupler, along the transmission line, through the coupling equipment at the far end, and into the receiver, which is set to the same frequency. As it passes through all this circuitry, the signal strength gets weaker, until at the receiver it may only be, say, 10 milliwatts. This loss of signal strength is known as attenuation. This signal has lost 9.99 watts of power en route. But I can hear you saying we always see signal loss referred to in terms of decibels. Even some of our instruments indicate in units of dB or dBm. What does this all mean? Well, for one, you know that the decibel is often used as a unit of sound. You will often see reference to 85 dB on the factory shop floor or 100 dB at aircraft takeoff. It would seem logical that telephone transmission and by extension any communication transmission would also be measured in decibels or dB for short. As used on carrier systems, the dB is actually a ratio comparing signal power into a circuit with power out, and by implication, an indication of loss. The expression is power loss in decibels equals 10 times the logarithm of the ratio power in over power out. The decibel is, of course, 1/10 of a bell, so the basic expression is bells equals log power in over power out. However, decibels are more convenient to use, as the values are normally quite low, so we must remember to multiply by 10. As you know, the logarithm is actually an exponent of 10 that is a power on the base of 10. This logarithmic curve shows the log value corresponding to different values of power ratio. I'm sure you all remember the basic numbers. The logarithm of 10 is 1, of 100 is 2, of 1,000 is 3, and so on. In our example, the ratio of power in over power out equals 10 watts divided by 0.01 watts equals 1,000. From our curve, the log is equal to 3, so multiplying by 10, the decibel value equals 30. In order to get a feel for the magnitude of these numbers, take a look at this table showing the relationship between dB and the power ratio, power in over power out. As you can see, a measured dB loss of 10 indicates a power ratio of 10. That means 90% of the signal is being lost. At 3 dB, the loss is 50%. At 20 dB, the loss is 99%. This means that a transmitted signal of 10 watts arrives at the receiver at 0.1 watt. That is 100 milliwatts only. The receiver is very sensitive and can work with very low power signals, say a few milliwatts, or even less, provided the signal is clean and undistorted. Unfortunately, this is not usually so. Operation of the power line provides a lot of interference or noise in contrast to the carrier signal. The noise comes from corona, system disturbances, line switching, storm effects, and so on. You will often see signal-to-noise ratio expressed in dB. A typical value will be 10 dB. That means the signal strength is 10 times that of noise. Signal voltage loss can also be expressed in dB, and some test instruments are calibrated to read dB directly. The calculation is a little different to that for power loss. The voltage loss in dB is equal to 20 times the logarithm of the voltage ratio, voltage in over voltage out. We can add the voltage ratio to our chart for corresponding dB values. Now let's look at some typical values of attenuation of signal strength as it passes from the transmitter and along the line to the receiver. In the transmission equipment, attenuation will be about 5 dB. In the coupling equipment, about 3 dB. We will lose about 3 dB through the line trap and a further 8 dB along the line in this particular example. Of course, line attenuation depends very much upon its length, also the line voltage and carrier frequency. Higher line voltage leads to lower attenuation, while higher carrier frequency increases the loss. At the receiving end of the line, the signal will be further attenuated by the line tuner, 3 dB, the coupling equipment, 3 dB, and the receiving equipment, 5 dB. So in this particular example, the total attenuation of the signal is 30 dB. What is this in terms of power? Well, if we started out with a signal of 10 watts, the power at the receiving end would be 10 milliwatts. Remember, the dB loss quoted for any particular item is a ratio of power in and power out of that equipment. So you could work out the actual power lost at each point. An advantage of the logarithmic figure is that the dB values can be added arithmetically in order to find the total dB loss. You will often see a reference to power output in terms of dBm, say 30 dBm. The M indicates a reference base of 1 milliwatt. To find out the actual power, we need to multiply 1 milliwatt by the original power ratio. From our chart, we see that for 30 dB, the corresponding power ratio is 1,000. So the 30 dBm power indication is equal to 1,000 times 0.001 equals 1 watt. Let's now move on to look at another source of attenuation. With frequency shift carrier protection, FSK, all of the equipment must be designed to transmit, convey, and receive the signals at several different frequencies, often simultaneously. This situation offers the potential for considerable loss of signal strength between transmitters and receivers located at the same end, but set to operate on different frequencies. Consider this arrangement. At station G, the transmitter is set to operate at 150 kilohertz. In this particular scheme, the FSK shift between guard and trip is 200 hertz down. This means that the carrier will transmit a continuous guard signal at 150.1 kilohertz, and this will key to a trip signal of 149.9 kilohertz when initiated by relay action. At station H, the corresponding receiver is set to receive at the mean frequency, 150 kilohertz. The bandwidth allows the receiver to respond to either the guard signal or the trip signal. In the other direction, the transmitter at station H is set to transmit at a mean frequency of 152 kilohertz. And similarly with the corresponding receiver at station G. The chosen frequencies are close enough together to use single frequency line coupling equipment and line traps. But with this arrangement, there is the potential for significant signal loss and interference from transmitter to receiver at each end. But how come? Aren't the transmitters and receivers fitted with filters tuned to their specific channel frequency? For example, 150 kilohertz on this transmitter and 152 kilohertz on this coupled receiver. Unfortunately, when the frequencies are so close together, some of the 150 kilohertz transmitted signal will leak through into the receiver. Even a very weak 150 kilohertz signal may interfere with the incoming 152 kilohertz signal and cause misoperation. In order to reduce this loss, the transmitter and receiver at each end are coupled through a hybrid unit before connection to the tuner and coupling capacitor. This schematic shows the simplest type of hybrid. The transmitter is connected to the upper terminal, and the signal is consequently applied to the upper half of the transformer winding only. This winding is center tapped through a 30-ohm resistor and a tunable LC circuit. This is tuned during commissioning to give minimum loss, typically about 3.5 dB. The received signal at a different frequency flows through the lower half of the winding and out to the receiver via the bottom terminal. This arrangement separates the two signals and reduces the loss. Other types of hybrids are used. Make sure you become familiar with your own installations. Study the manufacturer's bulletins and your company procedures. In many installations, an on-off channel may be installed in addition to FSK. This channel would be used for a different type of protection scheme, such as pilot protection or breaker failure protection. Adding this to our schematic, we see the transmitter at station G tuned to 154 kilohertz, as is its corresponding receiver at station H. And for protection in the other direction, the transmitter and receiver are tuned to 155 kilohertz. As before, a hybrid unit is required at each end to reduce signal loss. There may be yet another hybrid connecting the signals from on-off carrier and FSK carrier. The on-off channel is off for most of the time and is only triggered on under abnormal conditions, allowing the same frequency to be used for both transmitting and receiving blocking signals. This also allows the channel to be used for other forms of communication, such as voice, telemetry, or supervisory information, all in addition to its role in protection. Of course, the protection scheme always takes precedence and will interrupt other transmissions when required for protective relaying. And we'll be talking more about these additional channels in the next segment. For now, switch off the tape and review this material in your workbook. Up to now, much of our discussion has centered around outdoor equipment, namely the line traps, coupling capacitor, its grounding equipment, and the line matching unit. The actual carrier equipment itself is located indoors, connected to the LMU input via the coaxial cable. The components or modules of the carrier equipment vary considerably according to the manufacturer, the specific purpose, say on-off or FSK, the number of frequency channels, any audio signals. However, we should always expect to find certain basic components. First, the power supply. The carrier equipment is usually operated from the station battery, say 129 volts. Other arrangements exist where a 250 or 48 volt battery is used. There is also a PLC power supply available that will run off 120 volts AC. This requires the installation of an inverter so that the carrier can continue to operate from the battery during power outages. The power pack in the carrier provides the special voltages for the carrier electronics. Let's look now at the transmitter. The initial signal is produced in the oscillator mixer at precisely the desired frequency. Generally, quartz crystal oscillators are used, and these are quite easy to replace in case of a defect. This circuit is controlled by the incoming signal from the protective relaying scheme. This may switch the unit on, or in the case of FSK, switch frequencies. The next basic stage is to pass the oscillator signal through an amplifier in order to boost the power to, say, 10 watts, sufficient for transmission to the receiver at the far end of the line. The boosted signal will then pass through the output filter, which is tuned for the specified operating frequency. Finally, it will pass through a hybrid unit if fitted, and from here, via the coaxial cable, to the line coupling equipment. The receiver equipment is similar. First, the incoming signal passes through the hybrid, then the input filter. The signal may then be processed and fed into a discriminator or other similar device which recognizes the message and triggers action, such as breaker trip, alarm and annunciation, loss of guard signal alarm, telemetry, supervisory control. Of course, we're looking here at a very basic arrangement. Your carrier equipment will consist of many more modules, components, and facilities for monitoring and adjustment. Here is a typical example of a transmitter test panel. This allows for test and adjustment during the commissioning stage and later at regular maintenance periods. Initially, the various power supply voltages must be checked and adjusted, typically 36 volts, 48 volts, or other voltage levels depending upon the particular make and model. In order to check the power output of the transmitter, the coaxial cable is disconnected and replaced by a resistor to represent the load. With the transmitter switched on, we can measure the voltage across the resistor and easily calculate the power output of the transmitter. The transmitter is adjusted to provide the specified voltage at different conditions, for example, guard and trip signals. Often, an oscilloscope is connected to check that the output wave shape is free of distortion. A frequency counter is also connected across the transmitter output so that the specific frequencies can be checked at the same time and adjusted as necessary. Of course, here we're presenting just a general outline of tests to be performed. In practice, you'll have many more fine adjustments to take care of. Make sure that you follow each step laid down in your specific equipment instruction manual. And don't forget to remove the dummy load and reconnect the coaxial when the tests are completed. Now let's look at the other half of the carrier equipment, the receiver. Here is a typical test panel for a typical receiver. For this test, the coaxial input is disconnected, and instead a test signal of known frequency and power is fed into the receiver. The test signal is provided by a signal oscillator or signal generator. A frequency counter and RF voltmeter are also connected to monitor the signal. The tests and adjustments are usually carried out on power voltage supplies, the discriminator zero calibration, discriminator response for guard and trip frequencies, operating sensitivity to varying input signals, carrier level monitor, setting of alarms. Once again, you must become familiar with your own equipment and associated test procedures. In addition to test and setup of carrier equipment, the line coupling equipment must also be checked out and adjusted as necessary. We talked about this briefly in earlier segments of this tape. In general, the tests will include measurement of line trap impedance at different frequencies, insertion loss in dB between input and output of the line tuning equipment, reflection loss using a dummy load at the tuner output, reflected power measurement with transmitter and receiver in service. At this time, the final adjustment of the impedance matching transformer taps can be made. Measurement of signal loss end to end with the carrier in service and at different frequencies. Adjustment of trip margin at the receiver. You have observed that specific test equipment is required for setting up carrier systems. The essential devices are the frequency selective voltmeter. This registers the signal at the selected frequency only and disregards all other signals. The signal generator to provide a test signal at selected frequency. The RF voltmeter. The frequency counter. The reflective power meter. Once all of the carrier system has been aligned and is in service, trip tests must be conducted to ensure that the combined protection scheme and carrier system function correctly. This would include such protection schemes as FSK direct transfer trip, directional comparison blocking, and unblocking. These and many other forms of pilot protection were discussed in earlier tapes in this series. In planning and conducting these trip tests, cooperation with the operating department is essential, and all necessary permits to work must be taken out and safety procedures followed. Also, where multiple tests are to be performed, make sure to isolate the local tripping circuit for each breaker. Monitor instead the trip signals. Now remember, in this discussion we are only looking at a broad outline of carrier equipment and setup. You must familiarize yourself with your particular company installations and procedures. And always keep the equipment instruction manuals close at hand. Please switch off the tape now and review this material in your workbook. Many carriers include facilities for transmitting voice and other audio signals from end to end over the carrier system. The audio signal may be transmitted during the off period of an on-off system, or even across the guard signal on an FSK system. However, the transmission for protective relaying will always have priority and will disconnect the audio transmission when relay operation is triggered. Signals such as voice and telemetry all operate within the audio frequency band, usually between 300 hertz to 3,000 hertz, or 0.3 to 3 kilohertz, in relation to the carrier signal. This audio signal is mixed with the RF carrier signal in a modulator before transmission down the line. The mixed signal is then demodulated in the receiver at the other end, leaving only the audio signal. Suppose, for example, we wish to transmit a constant 1,000 hertz signal, perhaps for alarm purposes. This audio signal is superimposed on the high-frequency carrier signal, say 105 kilohertz, and modifies the amplitude of its wave. This is known logically as amplitude modulation, AM. Let's take a closer look at these waveforms. The modulated signal looks like this. You can see that when the carrier signal is removed by demodulation at the receiving end, only the audio wave remains, so the speech pattern can be recognized. Note that the amplitude modulation affects both sides of the wave and produces an envelope. When this signal is demodulated and analyzed, there are actually 3 frequencies present at any instant. The 105 kilohertz carrier is one. Another is the 105 kilohertz plus the audio signal frequency, 1 kilohertz in this example. That is 106 kilohertz. This is known as the upper sideband. In addition to this, there is one more signal, that is 105 kilohertz minus the audio equals 104 kilohertz. This is the lower sideband. With voice modulation, these upper and lower frequencies will be changing all the time within, say, 3 kilohertz up or 3 kilohertz down from the carrier frequency. The lower sideband is actually a mirror image of the upper band, just like the modulated signal envelope that we looked at. But only one of the sidebands is actually used after demodulation. So why do we need to transmit both upper and lower bands? Other people asked that same question and came up with the single sideband system. Here, both the carrier signal and the lower sideband signal are suppressed in the transmitter, and only the upper sideband frequency is transmitted, 106 kilohertz in our example. The advantage is that it requires much less power to transmit the signal. And for this reason, portable communications equipment is usually single sideband, as there is a considerable saving in weight and size. You'll find many power line carrier installations using single sideband or SSB transmission, providing audio communications in addition to protective relaying. For protective relaying, audio tones are superimposed on the carrier signal to provide FSK signaling. Usually, the SSB carrier operates within a bandwidth of 4 kilohertz to accommodate all of the various audio signals. For the usual two-way communication, a total bandwidth of 8 kilohertz is required. This could create something of a problem, as the available frequency spectrum becomes crowded with other users. LoRaN navigation, for example. As an example of SSB equipment, let's take a look at this installation. The complete carrier unit is made up of many interconnected modules, each with its own specific function. At the top left of the cabinet is the RF hybrid module. As you know, this is where the transmitter and receiver frequencies are segregated. The output from the hybrid is connected to the coaxial cable running out to the LMU in the switchyard. The hybrid needs adjusting during carrier installation to allow for actual line impedance. The next module in the panel is the supervision unit. It monitors three things: the transmitter current, the 15-volt power supply voltage, and the receiver's automatic gain control, or AGC, voltage. When the incoming signal is strong, the AGC turns down the amplification or gain of the input signal. Conversely, if the signal becomes weak, the AGC turns the gain up. The magnitude of the AGC voltage signal provides a useful indication of the quality of our power line carrier channel. If the gain is high, we must be receiving a weak signal, and vice versa. This next module, the transmitter filter, is a tuned circuit that passes only the transmitter's specified frequencies. With an SSB carrier, the filter blocks the lower sideband and carrier frequencies, allowing only the upper sideband frequencies to pass through. Incidentally, some single sideband units may retain the lower sideband and reject the upper, along with the carrier. The filter is provided with an impedance matching transformer with taps on the output. The second tier of equipment is devoted to power supplies for the carrier. It contains modules to filter or condition the incoming power, as well as modules to produce the special voltages needed by the electronics, typically 48 or 60 volts, and also a minus 15 volts. Moving down the carrier panel, the next three tiers contain the modules that make up the radio part of the carrier, both transmitter and receiver. This includes oscillators, which set the transmitter and receiver frequencies, modulators and demodulators to mix or demix voice and other audio signals, amplifiers, filters for outgoing and incoming signals. Maintenance of these units usually consists of test, identification, and replacement of defective components or modules. Voltage test points are accessible on the front panel so that defective modules can easily be identified. Special test sets are often provided by the manufacturer. This particular carrier has a Speech Plus filter. And what is this for? On this transmitter, the bandwidth actually ranges from 300 to 3,480 hertz. To be intelligible, the human voice doesn't require the higher frequencies on this band. As a result, PLC sets are often fitted with a filter that splits the audio baseband into two parts, the speech portion from 300 to 2,200 hertz, and the speech plus portion from 2,200 to 3,480 hertz. You can now use the speech plus band for various purposes, such as telemetry or relaying tones. Another special module or pair of modules is the compressor expander. The objective is to improve the clarity of voice communication. Much of the message transmitted by voice is in low-level sounds. The compressor compresses the dynamic range of the voice so that the weak sounds are transmitted at the same level as the loud ones. Then at the other end of the circuit, the expander does the reverse process so that the voice will sound normal. This technique also reduces the noise from line interference that is heard between syllables and words. An interesting feature of this particular carrier unit is the boost drop bus. Let's see how it works. Suppose the unit is used for voice plus 2 tones for line relaying and 3 tones for telemetry. We have to connect all of these inputs to the carrier's modulator circuit and assign voltage levels to each input. We can increase the modulator output voltage only so much, say 100 millivolts, before we run into the problem of overmodulation, where the final amplifier starts distorting. So typically the voice signal would be assigned, say, 50 millivolts, with 10 millivolts each for the remaining 5 tones. The voice and telemetry inputs are connected to the drop bus, while the relay signals are connected to the boost bus. Now, when a protective relay sends a trip signal through the tone equipment, this contact initiation also disconnects the drop bus from the modulator. At the same time, the boost bus modulation voltage is increased to 50 millivolts for each relay tone. We have now increased the important line relaying signals by a factor of 5 at a very small cost. Yearly inspection of these modulation levels is recommended. The potentiometers and amplifiers can drift, and the carrier could be over or under modulated as a result. Okay, in this tape, we've tried to take a broad look at different types of carrier systems and the main items of equipment. But this is only a starting point. You have to become familiar with the actual equipment installed on your own power system. Make sure you always have access to company procedures and manufacturer's instructions for this equipment, and use them. Please switch off the tape and thoroughly review the material in your workbook.